Hello, everyone. So today we're going to talk about line integrals, um, where C is a curve in R2 and R3, line integrals of scalar functions and vector functions. I'm going to talk about just a list of theorems from chapter 16.3 concerning conservative vector fields and numerous examples. So let's go ahead and get started. We have section 16.2 line integrals. So let C be a curve in R2, B given by x equals x of t, y equals y of t for t in the closed interval from A to B. So locally, because we have one variable as the parameter, locally this looks like this curve. Well, this curve looks like R, the real number line. So we're mapping a closed interval of R into a curve in R2 and then in R3. So f is a function of two variables whose domain is the curve C. So where does the graph of f live? And if anyone was here, I would wait for an answer, but no one's here, so I'll go ahead and tell you. If f is a function of two variables, mapping, this closed, this curve C, subset of R2, to R, then we have that f is in R3. And then, we have some notation. This is a right Riemann sum, I hope. I just kind of as I went, but so if we take the limit, we know this from single variable calculus. If we take the limit of the Riemann sum, we get an integral, and so we have this notation: the integral over C of f being a scalar function, ds, and ds is the differential element of our curve. But what if f of xy equals 1? That is, what if we had the integral over C of 1 ds? What does this calculate, and what is the formula? Well, I would revert you back to chapter 10.2 calculus. And recall the formula for ds. If we have, we have the integral from a to b ds. This was the integral from a to b of the square root of, well, x prime of t squared plus y prime of t squared dt. So now I supply a sketch of what this looks like. This line integral of a scalar function for arbitrary curve and function, and an analogy of what we're calculating. So here we have some couple pictures. So let me describe this in some words. So this is the x-axis, we have the y-axis, we have the z-axis. This curve lies on the xy plane, and then it's going up to the function. So another way to picture it would be if we had a flying bed sheet, that is our surface of our function f mapping R2 to R. And we have the curve lying on the xy plane beneath it, and we're going all the way up to the function. So the analogy is a fence. Finding the area of fence along path C up to the function f. So we can have a curve EC up to, f variable height. So the integral over C of f of xy ds is the integral over C of f of x of t, y of t, and then this portion is just ds, where we already know about ds. And remember, you could see ds. Well, you see it some commonly as 1 plus f prime of x squared dx, if this is a function of one variable. But remember that f prime is dy dx, so we have 1 plus dy dx squared times dx. Well, this, okay, I'm going to put the dx inside the radical. So then we have the square root. If I put it inside the radical, that means I have to square it. And what does this give us? Well, we distribute through, cancels with the bottom dx squared, then we get the square root dx squared plus dy squared, which is, x prime of t squared plus y prime of t squared ds. So now we can evaluate these with proper parameterizations. So we have example. We have page 1072. This is number 3. We have the integral over c of this function ds, where c is the right half of circle with radius 4. So let's go ahead. This is a line integral of scalar function over a semicircle. Let's go ahead and draw the semicircle. So we have 4, -4, the right half of it, +4. And to parameterize this, we need an x of t, we need a y of t, and we need t in between some numbers. So to parameterize any circle, well, to parameterize a unit circle, it's just cosine t sine t from 0 to 2 pi. But with this animal, we have equals the square of the sum of the squares equals 16. So we're going to have 4 cosine t, 4 sine t. Why does this work? Well, if I plug it into x squared plus y squared, I would get 4 cosine t squared plus 4 sine t squared equals 16. That's 16 times cosine squared t plus sine squared t equals 16. We have 16 equals 16. T lies in between. Well, okay, if we go clockwise from the positive x-axis, this would be negative pi over 2. Counterclockwise, pi over 2. So we have our parameterization. We have our t-bounds. So we can go ahead and evaluate. So if we have the integral over c of x y to the 4th ds, this is going to be the integral from negative pi over 2, pi over 2, x y to the 4th and then let's go ahead and calculate ds off to the side. So ds is the square root of x squared, which would be negative 4 sine t squared, or x prime squared, plus 4 cosine t, that's y prime squared. So this is equal to 16 sine squared plus cosine squared, which is just 4. Okay. Now this, we have 4 to the 4th, 4 to the 1st, 4 to the 1st. That's 4 to the 6th. The integral of negative pi over 2, pi over 2, sine to the 4th t, cosine t dt. Now this is a perfect u substitution. If we choose u to be sine t, then du has to be cosine t dt, which we have. Changing the bounds from u to t, we have negative pi over 2 to pi over 2. That would be from negative 1 to positive 1 with sine. Sine of negative pi over 2 is negative 1. Sine of pi over 2 is positive 1. So we have 4 to the 6th, divided from negative 1 to 1, u to the 4th du. This is 4 to the 6th over 5, u to the 5th, evaluated from negative 1 to 1. So then we get 4 to the 6th times 1 minus negative 1 is 2 over 5. And going to my calculator, 4 to the 6th times 2 divided by 5, we get 1638.4. Very nice. So now there's also some line integrals of f with respect to x. Notice that instead of dx, we have a dx. Instead of a ds, we have dy. Hence, well, you just plug in your parameterization for x and y and calculate dx. dx is x prime t dt. dy is y prime of t dt. So they frequently occur together, where we can write, if c is the same, one integral, and write it with your dx and dy. Okay, so let's go ahead and do an example. C consists of line segments from 0, 0 to 2, 1, 2, 1 to 3, 0. So we have 0, 0, 2, 1, 3, 0. It's going to look like this. So this is two curves, right? So we're going to split this up into two line integrals. So this is y1 equals x over 2. This is y2 equals, let's see, we're going to get, this is a slope of negative 1. We have intercept at 3. So then, proper parameterization, let's call this C1 of t equals t over 2. That's for y1, and then for y2, we have t, negative t plus 3. So then we have to think of some t bounds. T ranges in between, see, this is going to be 0 to 2. Over here, t ranges in between, let's see, we have 2 to 3. Okay, so then we have the integral c1 x plus 2y dx plus x squared dy plus integral of c2 x plus 2y dx plus x squared dy. So for C1, we're using this representation. For C2, that. Okay, so we're going to have the integral 0 to 2 of x is just t, plus 2y. Y is t over 2, so that's just t. Now dx is x prime of t dt. This is 1 dt. Plus x squared, well that's just t squared. Dy is just dt over 2. And we're adding the integral from 2 to 3 of t minus 2t plus 6 dt plus t squared times negative dt. All right. Now we get 2t plus t squared over 2 dt from 0 to 2. Okay, so this is negative t plus 6. So we have plus 2 to 3, negative t plus 6 minus t squared dt. Integrating, we get t squared plus t cubed over 6 plus negative t squared over 2 plus t minus t cubed over 3. Evaluating these two from 0 to 2, evaluating these two from 2 to 3. Okay, so then we get 4 plus 8 over 6, 0 zeros everything out, minus 9 over 2 plus 18 minus 27 divided by 3 is 9. Minus 4 squared over 2 is 2 plus 12 minus 8 cubed. 2 cubed is 8 over 3. So, okay, so we have 4. Well, 18 and 9, 18 negative 9 is 9 plus 4. 9 plus 4, 9, 10, 11, 12, 13. Okay, so we have 13 plus, divide by 2, 4 over 3 minus 2, 9 over 2, plus 2 minus 12 plus 8 over 3. 8 over 3, 4 over 3, 12 over 3. 12 over 3 is 12 divided by 3 is 4. And 4 plus 13, 17 minus 12 plus 2 minus 9 over 2. Okay. 17 minus 12 is 5. 5 plus 2 is 7. Minus 9 over 2. 14 minus 9 over 2. 14. 9, 10, 11, 12, 13. I'm getting 2. Is that right? Yeah, I think that's right. Let me check. Yeah, 2. 2 is correct. Okay. Oh yeah, it's just a little bit calculation heavy since we have 2 curves. Yeah, so a compact form of how we write this line integral arises from regarding the parameterization of C as the function, the vector value function R, so that the magnitude of R prime of t is exactly ds. Hence, we can write the line integral over C of f of xy ds as integral over C of f of R times R prime of t, with magnitude of R prime of t. So notice this is scalar. We're applying by something scalar because magnitude is scalar. Okay, let's look at line integrals in space. Given C with parameterization, x equals x of t, y equals y of t, and z equals z of t, and F maps C, a subset of R3, into R, we have the same thing. So let's look at an example. So C is a line segment from 0, 0, 0 to 1, 2, 3, and we're integrating this function of 3 variables. Okay, so let us find parameterization for C. So remember from earlier on in this class, we can parameterize a line by doing P naught plus TV. Well, if we choose P naught to be 0, 0, 0, that's just going to be the easiest. And remember, V was a slope vector between the 2 points. So we get 1 minus 0 is 1, 2 minus 0 is 2, 3 minus 0 is 3. So V is the same thing as the other point. So then our parameterization would have to be T times 1, 2, 3. Easy. So if we want to calculate the magnitude of R prime, well, first R prime of T is 1, 2, 3. Magnitude R prime of T is the square root of 1 plus 4 plus 9. 9, 10, the square root of 14 dt. All right, so that was ds. Then we just sub everything in. We're evaluating this integral from 0 to 1 because 0 would give us 0, 1 would give us the second point. A nice parameterization. So then we have x is 1t, y is 2t, z is 3t, and ds was the square root of 14 dt. So this is our integral. This is the integral from 0 to 1, t, e. Okay, so we got 2 times 3. Yeah, 6t squared, the square root of 14 dt. Square root of 14 can come out. It's a constant. Okay, now we do a u substitution. We get u equals 6t squared, du is equal to 12t dt. We don't have a 12. Divide by it. dt is equal to du over 12. The 12 can come out. The 1/12 can come out. Square root of 14 over 12, integral 0 to 1, e to the u, du. Integral of e to the u is just e to the u, evaluated from 0 to 1. So we get the square root of 14 over 12. E to the first minus e to the 0 is just 1. So we arrive at the answer. Okay, so now we have curve. Really, we're going to have to break it down into 2 curves. And then we have this animal. Okay. So let's think about this. If we have this is P, this is Q, we could call this R. If we integrate P with respect to X, we get xy plus xz plus g of yz. We integrate this one with respect to y, we get y plus yz plus h of xz. If we integrate this one with respect to z, we would get xz plus y plus j of xy. So then we can see j would be exactly xy, xz, or h of x comma z would be xz. And then we have g of yz would be yz. So then we would have a scalar function f of xyz equaling xy plus yz plus xz, so that the gradient is equal to what? Okay, if we take the gradient, the first partial of f with respect to x would be y plus z. First partial of f with respect to y would be x plus z. First partial of z or f with respect to z, x plus y. But we don't need that problem. It's a good thing to know for the future. Okay, so let's work on evaluating this line integral. 0, to 101. Well, we can parameterize that, no problem. So like R1 t is t times 101. Now R2 is a little bit trickier because we have a point, and then we have plus t times 0 minus 1 is negative 1. 1 minus 0 is 1. 2 minus 1 is 1. So then we get that this is going to be, the parameterization is 1 minus t, t, 1 plus t. So we have two segments to deal with. First guy being from t is 0 to t is 1. Second, I think we set it up and so that could be the same. Plug in 0, we get the first one. We plug in 1, we get the second one. So this is see the integral c1 0 1 y. Let's looking at this guy. Y is 0. Z is t. Dx is just dt plus x, which is t, plus z, which is t, times dy, which is 0 dt, plus x plus y, that's t plus 0 is t, dz is dt. And now we add c2, 0, 1, we get y plus z, that's y plus 1 plus t, dx is negative dt. Okay, now we have plus x plus z, x is 1 minus t, z is 1 plus t, dy would just be dt, plus x plus y, t minus 1 plus t is 1, dz is just dt. Okay, these t's cancel. This is actually 2 dt. We have the same bounds on both of them, so we can proceed as one integral. So then we have t plus t, that's 2t. And then we have minus, this is a minus right here, so we're going to pull out the dx, minus 2t, minus 1, plus 2, plus 1, dt. Okay, these cancel. Integral of 2 dt is 2t, evaluated from 0 to 1 is 2. one thing I forgot to mention. So we've already done this. I briefly said something about it, but if we have one curve, C1, say from A to B, then we have like another curve. We call this C1, C2, and then, well, we call the from here all the way to here, we call that C, the rule of f of xy ds. Well, this guy is actually just C1 f of xy ds plus C2 f of xy ds. You break it up into two separate integrals. Okay. Now we have line integrals of vector functions. So those were all line integrals of scalar functions mapping Rn to R. Now we will look at line integrals of vector fields. So we're going to evaluate the line integral over C of big F dot dr with vector notation. C is given by vector value function of R. So you can see that instead of multiplication between F and ds, we have a dot product between F and dr, which is another type of multiplication. So how do we do this? Well, the integral of C F dot dr is equal to integral of C F of R of T dot product with R prime of T dt. So we can go ahead and do this. They're given T bounds. You just plug everything in. We have 0 to 1. Okay, so F of R, that's going to be, okay, so we have sine of x. X is T cubed. Cosine of y. Y is negative T squared. But cosine of a negative number is just the positive because it's an even function. So cosine of negative T squared is cosine of T squared. From trigonometry, cosine is an even function. If it were sine, well, sine of a negative number is negative sine of that number. And we have x times z, x times z, e to the fourth. Now taking the dot product of r prime, that's 3t squared negative 2t 1 dt. We can do that. So taking the dot product component-wise multiplication, we have 3t squared sine of t cubed plus, well, actually that's a minus 2t cosine t squared plus t to the fourth dt. All right, if we do u substitution, u is equal to t cubed du. Perfect. We do v is equal to t squared, then dv is what? 2t. You don't need a substitution right here. You can just integrate that directly. Okay, so now we get bounds. So u, t is 0 to 1, u is 0 to 1, t to v, t is 0, 1, v is 0, 1. So then we get the integral 0 to 1 sine of u du minus the integral from 0 to 1 cosine v dv plus t to the fifth over 5 ever evaluated from 0 to 1 So the integral of sine is negative cosine. The integral of cosine is positive sine. Fundamental theorem of calculus down there. Okay. So cosine of u evaluated from, well, negative cosine. So we have negative cosine 1 minus negative cosine of 0. This just turns into positive 1 minus sine of 1 minus sine of 0. Sine of 0 is 0 plus 1/5. We have 1/5 plus 1, 6/5 minus cosine of 1 minus sine of 1. Okay. Laundry list of theorems from chapter 16.3. That is the fundamental theorem of line integrals. So if we let C be a smooth, continuous curve given by the vector function r of t for t in the interval from a to b, let f be differentiable function whose gradient vector, the gradient of f, is continuous on C, then the integral over C of del f dot dr. Remember, del f, so if f maps r into r is a scalar function, then the gradient of f is a vector function mapping Rn to Rn. So this del f, this is really a vector field, a gradient vector field, a special type of vector field. Then we just plug in the endpoints into the little f, right? That is r of b, f of r of b minus f of r of a. Look at it like this. This is the integral of a derivative. The integral of a derivative is just the function that you're differentiating. You look at it from the scope of single variable calculus, integral of a to b, f prime of x dx is f of b minus f of a. It's the same thing. Line integrals of conservative vector fields are independent of path. The line integral of the f dot dr is independent of path in D if and only if the integral over C of f dot dr equals 0 for every closed C in D. So we're going to come to the conclusion that gradient vector fields are conservative, hence independent of path. So we get to the question of why is this integral 0 when it's closed? Well, okay, if we look at it this way, we have, some, let's just draw it like this. We have some closed curve, closed meaning the endpoints are the same. Well, if we use this logic right here, then we'll just get f of r of b minus f of r of a, where r of b and r of a are the same. So we get f of xyz minus f of xyz. That will necessarily be 0 because it's the same f at the same points. Suppose f is a vector field that is continuous on an open connected region in D. If the integral of f dot dr is independent of path in D, then F is a conservative vector field on D. What is a conservative vector field? Oh, I wrote it right there. There exists an F such that the gradient of F equals big F. And that's what we did with this past example right here. This guy. So if we write big F as y plus z, x plus z, x plus y, well, we already thought of a function f of x, y, z, and that was xy plus yz plus z, y, because when I take the gradient of this f mapping R3 to R, I get f maps R to R3 to R3, such that we have, this equality that gradient of f is equal to big F. So big F is conservative. If I give you line segments, suppose I gave you like a circle, an entire circle. It loops around and comes back to the circle from, like let's say the unit circle or something. Yeah, that would be the parameterization if I gave you R of t equals, and it could be something like this. It could be cosine t, sine t, and then say it was shifted up 1 unit for t in the interval from 0 to 2 pi, then it would be 0. Because it's a conservative vector field. Here exists a scalar function such that the gradient of the function equals our vector function, and the curve is closed. So then by this theorem, we would have that integral would evaluate to be 0. Okay? So if big F of xy equals P of xyi plus Q of xyj is a conservative vector field with P and Q having continuous first order partial derivatives on D, then throughout D, Py is equal to Qx. Look at it this way. So F is conservative. There exists a scalar function such that the gradient of the scalar function equals big F. So then we would have F, well, we would have like del F is equal to Fx, Fy. But they called Fx, they called this P and this Q. And then the claim is that Py is equal to Qx. Well, Py is F of x, y, Qx is F of y, x. But we already knew that was true. Where have we seen this before? That with Clairaut's theorem. We have equality of mixed partial derivatives when they're continuous. Notice we put the constraint on P and Q to be continuous first order partials. That would be the same as putting the constraint on the scalar function to have continuous second order partials. Okay? So F equals P I plus Qj, vector field on an open simply connected region D. P and Q have continuous first order partials, and we have that Py equals Qx, and F is conservative. I think I have a small example coming up next. See, what did I do? Oh, I worked it out right here. Well, I guess I'll just erase it and do it again. So we have the big F of xy equals y e to the x sine of y. Why don't I just do this? Hit delete. Yeah, let's do this. Ha, gone. Okay. Now we're gonna where this vector field is conservative, we're gonna show it. So we got p of xy equals y to the x plus sine y. We have q of xy equals to the x plus x cosine y. Okay, what is p sub y? P sub y is to the x plus cosine of y. What is x? Qx is to the x plus cosine y. Notice that py is equal to x. So it's conservative. This is a conservative vector field. That is, any line integral in it is independent of path, and it would just evaluate to being the scalar function evaluated at the endpoints. If the path was closed, then it would be 0. Why? Well, because the endpoints are the same, so it would be evaluating the function at the same value and subtracting them, making it 0. So let's go ahead and find little f. Little f such that the gradient of f is equal to big F. Well, what are we going to do? We're going to see that okay, so let's think about this. The gradient of f is equal to f sub x, f sub y. So p is f sub x, q is f sub y. We're going to take p and integrate with respect to x. And we're going to do the same thing with q. Okay. So the integral of e to the x is just e to the x. The integral of sine y is just x sine y. Now the integral of q, where q is e to the x plus x cosine y, integrated with respect to y, what do we get? Oh yeah, don't forget to add your function of integration, g of y. Then we get y e to the x. The integral of cosine is positive sine, so we get x sine y plus h of x. Notice that every term matches. So our g of y and h of y just be arbitrary constant, a scalar constant, not a function constant. So then we get f of xy is equal to y to the x plus x sine y. All right, guys, that is everything I have prepared for today. So I hope this aids you in your quest for knowledge. And thanks for watching. See you later.